Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering our last and final lecture for this playlist, and it's going to be all about electrochemistry. In this chapter, we're going to cover three main objectives. First, we're going to talk about electrochemical cells. We're going to explore galvanic and electrolytic cells. And we're also going to talk about electrode charge designations. Second, we're going to move into cell potentials. We're going to examine reduction potentials and the electromotive force so that we can have a clear understanding of how they influence cell performance. Last, this section will cover the relationship between electromotive force and thermodynamics, including Gibbs free energy and reaction quotients. In addition, we're also going to explore electrochemical stoichiometry. With that, let's go ahead and get started with our first objective. Electrochemical cells are contained systems where redox reactions occur. These cells can be classified into three main types. First, we have galvanic cells, also known as voltaic cells. Then we have concentration cells and electrolytic cells. First, we're going to discuss galvanic cells and concentration cells together because they both involve spontaneous reactions. In a galvanic cell, a spontaneous redox reaction generates an electric current. This means that the reaction can occur naturally without any external energy input, and it produces a positive electromotive force. It produces a positive EMF. The EMF is the voltage or the electrical potential difference of the cell, and a positive EMF indicates that the cell can release energy, so delta G is less than 0. Common examples of galvanic cells include the batteries used in flashlights and other everyday devices. Concentration cells. They are a specific type of galvanic cell where the electrodes are identical, but the electrolyte concentrations differ. The difference in concentration drives the movement of electrons, generating an electric current. Like galvanic cells, concentration cells also produce a positive EMF, and they involve spontaneous reactions. Now, in contrast, electrolytic cells involve non-spontaneous reactions. These cells, they require an external power source to drive the chemical reaction, resulting in a negative EMF, which means they absorb energy, and delta G is greater than 0. A typical example of an electrolytic cell is the electrolysis of water, where electrical energy is used to split water into hydrogen and oxygen gas. Now, to understand how these cells function, it's crucial to discuss the concept of electron flow. In all electrochemical cells, electrons flow from the anode to the cathode. The anode is where oxidation, loss of electrons occur, and the cathode is where reduction or gain of electrons happens. It's important to note that while electrons flow from the anode to the cathode, the current is conventionally considered to flow from the cathode to the anode. This can be confusing because in physics, current is defined as the flow of positive charge, which is opposite to the direction of electron flow. But the takeaway points are, so that you don't get confused, is that while electrons flow from the anode to the cathode, conventional current flows from the cathode to the anode. Conventional current flow refers to the direction of positive charge flow. In circuits, it's defined as flowing from the positive terminal, the cathode, to the negative terminal, the anode, opposite to the actual flow of electrons. Now, finally, it's important to also discuss factors that can affect the performance of batteries, such as temperature. Temperature changes can significantly impact the efficiency and functionality of electrochemical cells. So, for example, lead-acid batteries in cars, which are a type of galvanic cell, they often fail in cold weather. This is due to the fact that low temperatures can slow down the chemical reactions within the battery, reducing its ability to generate current. We're going to explore the thermodynamics reasons behind this in more detail in Objective 3. But with this background information and this foundational understanding of the 3 different types of electrochemical cells, let's get into more details. We're going to start with discussing galvanic cells, specifically the Daniell cell, a little bit more. The Daniell cell is a classic example of an electrochemical cell that derives electrical energy from spontaneous redox reactions. In a Daniell cell, the setup includes 2 electrodes and an electrolyte solution for each. The anode, where oxidation occurs, is made out of zinc. During the reaction, zinc metal loses electrons to form zinc ions, and these electrons are then released into the external circuit. On the other hand, the cathode, where reduction takes place, is made out of copper. Copper ions in the solution gain these electrons to form copper metal. Now, the Daniell cell also includes a salt bridge. This is a crucial component that maintains electrical neutrality by allowing the flow of ions between the 2 half cells. Now, the salt bridge, it typically contains a salt solution like potassium nitrate, and it does not react with the cell components. Instead, it completes the circuit and it allows the cell to function continuously. Now, each half cell in the Daniell cell contains an electrolyte solution. The zinc half contains zinc sulfate, and the copper half contains copper sulfate. As this zinc undergoes oxidation at the anode, electrons are produced and they travel through an external wire towards the copper cathode, which can power an electrical device. At the cathode, copper ions gain these electrons and they're reduced to copper metal, which deposits on the cathode. Meanwhile, the salt bridge, it allows negatively charged ions to move into the anode compartment and positively charged ions to move into the cathode compartment to maintain charge balance. Electrons, they flow from the anode to the cathode, while the current by convention flows from the cathode to the anode. This movement of electrons and ions generates an electromotive force, typically around 1.1 volts in a Daniell cell. So if we scroll down here, we can see what we just described for the zinc half cell and the copper half cell, and they both have a EMF associated with them. From that, we can calculate the electromotive force. Like we said, it is typically around 1.1 volts in a Daniell cell. This positive EMF indicates that the reactions are spontaneous, as shown by a negative change in Gibbs free energy. Delta G is less than 0. Now we're going to discuss the calculation of cell potential in the second objective, but for now, appreciate that the calculation can be accomplished by knowing each half reaction like we see here. When we add the 2 half reactions, we get the net overall reaction. Now, another important point to make here is, again, electrons flow from the anode to the cathode in all types of electrochemical cells, and this principle holds for both galvanic cells and electrolytic cells, although the context and the driving forces between these 2 types of cells differ. In galvanic cells, which involve spontaneous reactions, the anode is negatively charged and the cathode is positively charged. Electrons naturally flow from the anode to the cathode due to the spontaneous redox reaction. So in summary, galvanic cells, like the Daniell cell, are fundamental in understanding how batteries store and release energy, and how they power various devices from flashlights to smartphones. Now, before we move on to the next type of cell, let's quickly talk about something very important called cell diagrams. A cell diagram is a shorthand notation that's used to represent the reactions in an electrochemical cell, and it provides a concise description of the cell's components and their arrangement. So for example, the cell diagram for the Daniel cell is written right here. This notation, it follows specific rules to convey information about the cell structure and its function. What are those specific rules? Well, to construct a cell diagram, one must list the reactants and products from left to right. You start with the anode and its corresponding solution, and then that's followed by the cathode solution and ending with the cathode itself. In the case of the Daniel cell, zinc serves as the anode, so it's listed first, and copper is the cathode, it's listed last. Now, this first half that we see right here, it shows solid zinc separated by a vertical line, and then zinc ions and their concentration. This indicates the oxidation of solid zinc to zinc ions in solution at the anode. And here in the second half, we see copper ions and their concentration separated by one vertical line and then solid copper. This represents the reduction of copper ions to solid copper at the cathode. Now, within the cell diagram, a single vertical line denotes a phase boundary. It separates different states of matter or phases of substances. A double vertical line indicates the presence of a salt bridge or another type of barrier that separates the two half cells. The salt bridge allows ions to flow between the solutions, and it helps maintain electrical neutrality without mixing the solutions directly. So in short, the following rules are used in constructing a cell diagram. First, the reactants and products are always listed from left to right in this form right here. All right, this is a very important form. Remember this for cell diagrams. The second rule is keep in mind that a single vertical line indicates a phase boundary, and the third rule is that a double vertical line indicates the presence of a salt bridge or some other type of barrier. Now that we understand cell diagrams, we can move into discussing electrolytic cells. An electrolytic cell is an electrochemical cell that uses electrical energy to drive a non-spontaneous chemical reaction. Unlike galvanic cells, which generate electricity from spontaneous reactions, electrolytic cells, they require an external power source to operate. These cells, they're essential in various industrial processes, such as electroplating and the electrolysis of water. In an electrolytic cell, there are two main electrodes. You have the anode and the cathode, similar to a galvanic cell. However, the roles of these electrodes are determined by the direction of the applied current. So in an electrolytic cell, the anode is the positive electrode. This is where oxidation occurs, meaning that the electrons are removed from the species at the anode. And despite being positively charged, it's still the site of oxidation. Now, the cathode is the negative electrode where reduction occurs. Electrons are supplied to the species at the cathode, enabling reduction reactions. Now, in an electrolytic cell, the electrolyte is a medium that allows ions to move between the electrodes, completing the electrical circuit. It can be a molten salt or an aqueous solution that contains ions. In addition, an external power source, such as a battery or a power supply, is necessary to provide the energy that's required to drive this non-spontaneous reaction. This power source forces electrons to flow from the anode to the cathode. Now, as an example, let us look at the electrolysis of molten sodium chloride. This is a fundamental industrial process that's used to produce sodium metal and chlorine gas. This process, it occurs in an electrolytic cell where an external power source drives the non-spontaneous reactions. In this process, molten sodium chloride, it serves as the electrolyte. When sodium chloride is in its molten state, it dissociates into sodium ions and chloride ions. An external power source like a battery, it provides the necessary energy then to drive the electrolysis process. Now at the cathode, sodium ions are going to gain electrons to form sodium metal. The reduction reaction occurring at the cathode can be represented like so. This reaction, it takes place at the negative electrode where sodium ions are reduced by gaining electrons. Now, at the anode, chloride ions lose electrons to form chlorine gas. This can be represented by the following reaction. So this oxidation reaction can be represented as follows. This reaction, it occurs at the positive electrode where chloride ions are oxidized by losing electrons. Now, the overall reaction for the electrolysis of molten sodium chloride is going to look like this. 2 sodium chloride, is going to form 2 sodium plus chlorine gas. This equation shows that molten sodium chloride is decomposed into liquid sodium and chlorine gas when an electric current is applied. This cell, again, is used in industry as the major means of sodium and chlorine production. Now, we've covered a lot in regard to electrolytic cells. It's also going to be important to discuss a little bit about who defined the principles governing the behavior of electrolytic cells. And that man is Michael Faraday. Michael Faraday was a pioneering scientist whose work in the early 19th century laid the foundation for the field of electrochemistry. He formulated the laws of electrolysis, which describe how electric current interacts with chemical substances to drive non-spontaneous reactions. Faraday's laws quantitatively relate the amount of substance altered at an electrode during electrolysis to the quantity of electric charge that's passed through the substance. He established 2 key laws of electrolysis. The first says that the amount of chemical change produced by an electric current in an electrolyte is directly proportional to the quantity of electricity that's passed through the electrolyte. The second law says that the amounts of different substances liberated by the same quantity of electricity passing through the electrolyte are proportional to their equivalent weights. This means that different substances require different amounts of electric charge to be deposited or dissolved. Now, a crucial concept introduced by Faraday is the Faraday constant, which represents the charge of 1 mole of electrons. It is a fundamental physical constant that is used in various electrochemical calculations. The value of Faraday's constant is approximately 96,485 coulombs per mole of electrons. This means that 1 mole of electrons carries a charge of approximately 96,485 coulombs. Now, using Faraday's laws and the Faraday constant, we can derive the electrodeposition equation, which relates the amount of substance deposited at an electrode to the electric charge that's passed through the electrolyte. This equation is given right here, where mole M is the amount of metal ion being deposited at a specific electrode, I is the current, T is the time, N is the number of electron equivalents for a specific metal ion, and capital F is Faraday's constant. This equation can also be used to determine the amount of gas liberated during electrolysis. Now, the best way to understand this equation and how to use it is to jump into a practice problem. This example asks what mass of copper will be deposited in a Daniell cell if a current of 2 amperes flows through the cell for 3 hours. To solve this problem, we're going to use our electrodeposition equation because it helps us determine the number of moles of element being deposited on a plate. And once we figure that out for copper, we can then convert it to mass. So what do we know? What are we given? We're given the current, it's equal to 2 amperes. We're given the time, equal to 3 hours. Of course, we want this to be in seconds. So 1 hour is equal to 3,600 seconds. For 3 hours, that's going to be equal to 10,800 seconds. We're also given N. We know that this is a Daniell cell, and a Daniell cell uses a copper electrode in copper sulfate solution. And because the oxidation state of copper in solution is +2, then N is equal to 2. And we know Faraday's constant, so we can go ahead and begin to plug things into our equation to calculate mole M. The current is 2 ampere. The time is 10,800 seconds, and that's going to be divided by N. N is equal to 2 moles of electrons, and that's multiplied by Faraday's constant, which is 96,485 coulombs per mole of electron. If we calculate this, we're going to get 0.11 mole of copper. Now we need to convert this to the actual mass of copper being deposited. We're going to use the molar mass of copper, which is equal to 63.5 grams per mole. And what we're going to get for the mass of copper is equal to 7.11 grams. And so there we have it. That is our answer to this example. Now that we've covered the fundamental differences between galvanic and electrolytic cells, let's focus on how the charge on the electrodes and the movement of ions are determined by the type of electrochemical cell. The charge on an electrode depends on whether we're dealing with a galvanic cell or an electrolytic cell. In a galvanic cell, also known as a voltaic cell, the anode is negatively charged because it serves as the source of electrons that move through the external circuit. The cathode, on the other hand, is positively charged because it attracts these electrons. In an electrolytic cell, however, the roles are reversed. The anode becomes positively charged, and the cathode becomes negatively charged. This difference arises because electrolytic cells require an external power source like a battery to drive the reaction. Despite this reversal in charge, though, one principle remains constant across both systems, and that is that oxidation always occurs at the anode and reduction always occurs at the cathode. To remember this difference, we can use a helpful matrix for assigning signs. So in this matrix, A stands for anode, C stands for cathode, E represents electrolytic cells, and V represents voltaic or galvanic cells. When the letters A and C are placed alphabetically across the top, and E and V are placed alphabetically along the side, then the positive signs fall on the diagonal. This means that in an electrolytic cell, the anode is positive and the cathode is negative. In a voltaic or galvanic cell, the anode is negative and the cathode is positive. So the goal of this matrix is to help you properly assign charges to the electrodes depending on what kind of cell you're dealing with. And with that, we're going to go ahead and end the lecture here. In the next video, we're going to start on objective 2. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.